This is a Maytech F765 wing flight controller, just one of many types of flight controllers you'll find on the market. This is an older one that's not made anymore, but this is the one I'll be looking at today just to give you some insight into what a flight controller is and how it works. Now, inside every flight controller is a microcontroller, and it's important to understand, useful to understand what a microcontroller is and how it works to understand what a flight controller does. And if my camera ever gets into focus here, you can see that this big chip right in the center of this board is the heart of the flight controller. It's an STM32F765 microcontroller, and it's made by a company called ARM. And that's where the F765 wing flight controller gets its name from, because it's based on this F765 microcontroller chip. So what is a microcontroller? Well, you can see that it's just a microchip, and around all four sides of this thing, it's got a whole bunch of pins. These pins are for input and output operations, and the board that it's mounted on gives connections to all these pins for the various functions and features that it provides. The microcontroller itself is a bit of hardware that is driven by a program that is programmed into the chip into flash memory. It's a form of non-volatile memory that hangs around when the power's off, so that when you turn on the power, that's the program that your chip is running. And there's flight controller software that you can load onto this chip, one of which is iNav, and another one, for example, is ArduPilot. iNav is popular among hobbyists. There's a learning curve up front for any of these things, but iNav is a quicker entry into using flight controllers if you're just getting started. And again, it's useful to understand what the microcontroller is and what it does for you to understand how things are connected and how they interconnect with the device. You can see on here there's a USB port here, and that's just one of the connections to this chip. So this chip supports a USB serial input connection, and it's probably routed through what's called a UART or a USART. A UART is an acronym for a Universal Asynchronous Receiver Transmitter. A USART is a Universal Synchronous Asynchronous Receiver Transmitter. And that just means that it's configurable. It can be synchronous or asynchronous. Most often you'll just hear it referred to as a UART. And all that boils down to is that it's a serial port. So there's a transmit and receive line for communicating bidirectionally through this port. So you can read and write to and from this port. So the USB is just a serial interface that's routed through one of the UARTs on the chip. And then the software or the firmware that's running on the chip will know how to process the information that's coming across. So there's typically a number of UARTs on a microcontroller. There are many different microcontroller chips that you can find on the market by different companies like ARM, Microchip, and others. And this particular chip is from the STM32 family, which is a 32-bit chip. So inside this chip is a processor, a microprocessor. I'm not sure what the actual term is, whether it's it's an MCU, microcontroller unit, I don't know. I don't remember. I should know this. But this is the STM32 family of chips, and it's F765. And if you look up the specs for this chip, you can see all the peripherals that are provided in it. And a peripheral is just an internal circuit. So this microchip has a bunch of microscopic circuits engraved and encoded into the silicon substrate of which it's made to provide the different input and output pathways into and out of this chip. So a peripheral is something like the microcontroller itself, the MCU. That's what is executing the code that's programmed into the flash memory on this chip. The flash memory could be considered another peripheral. It's just something that's on the chip. The UARTs are all peripherals. And then there's other things like an analog to digital converter. There's PWM generators. PWM is pulse width modulation, which is typically used by servos, and it will spit out a pulse varying from 1 millisecond wide to 2 milliseconds wide to determine the position of a servo. So there's various inputs and outputs on here. Another serial output or serial interface is the IIC or I2C or I2C. You may see it referred to in any of these references, which is just a two-wire protocol. It's similar to a UART, but it's different in how it works. It's more like a bus. You can connect multiple external peripherals or devices to an I2C bus, as opposed to a UART, which will connect to a single device. So you have a number of UARTs available depending on what chip you have, and the more UARTs that you have, the more devices that you can connect to it. And typically you'll connect devices through UARTs such as the GPS, airspeed sensor. I'm drawing a blank. There's any number of sensors that you can connect through the UART, including your receiver. Your receiver may be running S-Bus or Crossfire or some other protocol that will come through a UART. So all these pins on the chip itself are routed through the PC board to various pins on the board itself. So the particular board that the microchip is mounted on provides access that's convenient and useful for use in a flight controller application. The microcontroller can be used in any kind of device depending on what you're creating, but the manufacturers of flight controllers have broken out all the peripherals in such a way that makes it convenient for the types of components that you will have on a flying vehicle. You can use it even on a ground vehicle. But as you see on this board, if my camera will focus, a lot of the pins are labeled here as to what they are. So you can see like TX4, RX4, that's a transmit and receive for UART4. And there's a TX6 and an RX6 for UX6. And likewise for the UART2, UART7. So we can see that this board has at least 7 UARTs. All 7 UARTs may not be exposed on the board itself. You may not have access to all of them. You may only have access to a few. And I can see just looking at this, there's UART 1, 3, 7, 2, 4, and 6. So UART 5 I'm not seeing. So that might be used internally somewhere else. Although over here I see an RX5, which may be indicative of UART 5. But all these different pins have various functions. And out over here are servo outputs. So these are like PWM outputs, or I think it may also support digital servos, which means you'd be sending a binary command to the servos. Now, the nice thing about Maytech is that they have some really good documentation for their flight controllers. So you can look at this online and it'll give you information about what all is available on the board. And on the first page here, it indicates that it's the STM32F765 flight controller, and it has this IMU, which is an inertial measurement unit, which is built in, which is probably tied into a UART or some other input. It has a built-in barometer, the BMP280. So these are useful things for a flying aircraft. An IMU is an inertial measurement unit which measures rotation and movement laterally in the X, Y, and Z axis. So that gives you the orientation of your aircraft and its movements and whatnot. Barometer is used to indicate your altitude. And then there's an OSD built into this board, which is on-screen display, which will give you telemetry information on your video output, which is typically connected to a video transmitter so that you can receive the video signal on the ground if you're doing FPV flying, which is first-person view. So you can see all the telemetry displayed in text and numbers overlaid on the video. So that's what the OSD is. There's also a black box with a micro SD card slot built into the board. If you look on the side of the board, you can see that there is a slot there. It's hard to see, but you can plug in a SD card and it'll record flight data on there. So the flight controller firmware is utilizing that to write data to that memory card. And then if something happens after a flight, you can retrieve the memory card and stick it into a computer and load up some special software to interpret the data to see what happened. So all that's built into the board. That's not part of the microcontroller, but the microcontroller will have the firmware written to interact with all of these devices. So these are onboard devices. In the microcontroller itself, this one has 7 UARTs, as we kind of inferred from looking at the marking on the board itself. So 1, 2, 3, 4, 6, 7, and 8. So that goes up to 8. So UART 5 is used somewhere internally. That's why we didn't really see it. Soft serial is kind of like a UART that's implemented in firmware. So it acts like a UART, but it's not implemented in hardware like these other 7 UARTs are. You can simulate it in firmware. So there's an option there to create one of those. And in the flight controller software, such as iNav, there's an option in there that you can enable that to utilize that if you don't have enough UARTs to drive all your other devices. I've never run out of UARTs, frankly, because I don't do anything highly complex with my flying machines, but that option is available to you. Now there's 12 PWM outputs. So inside that microcontroller is all these peripherals. So you can connect up to 12 servos, for example. S1 through S10 here, it says supports D-Shot. D-Shot is some sort of digital protocol, I think. I'm not familiar with that, so you'll have to look that up to see what that means. But this microcontroller also has 2 I2C or I2C bus connections, peripherals. There are 6 ADD converters, analog to digital converters. And they're indicated as VBAT, which typically measures your voltage of your battery. The current, typically there's also a current sensor mounted on the board to make it convenient for reading the current draw of your system. RSSI is a received signal strength indication unit. I haven't used it, I'm not familiar that much with it. Analog airspeed, VB2, CU2, I don't even know what those things are, but these are all things that are available. You can look them up to see if you need them or how to use them. Then there's also a SPI4. SPI is serial peripheral interface or something like that, serial protocol. It's another 2-wire interface like I2C, but it uses a different protocol, and I'm not sure what even that's used for. I've never used it. But it's good to know just what all is provided in this board. Now on the board itself, there's switchable dual camera inputs. You can connect two cameras to it. Switchable power for camera, 5 volts, 9 volts, or 12 volts. And then there's typically a power board, like a BEC, battery eliminator circuit. So it provides 9 to 32 volts DC in, so you can support up to 3 to 8S LiPo battery input. It's got a current sensor, as I mentioned, up to 132 amps. It has a 5 volt 2 amp BEC, a 9 volt 2 amp BEC, and a 8 amp variable, and that's probably selected between 5, 6, or 7.2 volts. So VX can be selectable depending on how you configure the board. I'm sorry if I'm running out of the frame here, I'm looking at the paper. And then there's, I don't even know what this is, LDO 3.3 volts, 200 milliamps. So that's just an overview of what is in this flight controller. As mentioned, Maytech has a lot of good information in their documentation about what's what. They give you more information. If you're running iNav, how it's laid out. It's using, by the way, there's internal timers that are also peripherals. Timers are just something that either defines a periodic clock or time, records the time of an event or whatever. But there's information you can look through to find out more about how the board is laid out and how you hook it up. So these diagrams are very useful when it comes to wiring up your system for your particular model. Here there's a beeper. There's an audible beeper. If your airplane goes down, that's useful to have. It's also used for communication when you're setting up your flight controller. It'll beep in various configurations to let you know what's going on. For example, when you arm your aircraft, it'll beep a certain way. When you get a GPS lock, it'll beep a certain way. When it's ready to launch, it'll beep a certain way. And if it's in fail-safe, it'll beep an SOS. So the beeper is useful for communication as well as locating a downed aircraft. Now, it's not super, super loud. You can't hear it at a great distance unless it's really, really quiet outside. But it is useful when you get close to where your aircraft is. You might hear it and find your aircraft in the grass if you've gone down somewhere. But it shows you how to hook up, how and where to hook up your GPS. And there's an OLED display here, analog airspeed, digital airspeed perhaps. And there's like a servo controller board you can hook up. Your ESCs, you can drive up to 2 ESCs on this board, and then all your servo outputs and your camera and transmitter. It doesn't show the transmitter, does it? Camera 1 and camera 2 input, you can switch between the two. And somewhere there's the transmitter. Maybe this is the video transmitter. I haven't really, yeah, this is a video transmitter. Sorry, I thought that was a serial driver. So it shows you where to hook everything up. And it lists all the, like, ground power, RX6, TX6, and these are suggested inputs. You can switch them around in some cases, like my GPS and my receiver. I have swapped those inputs just because of physically where they were in my aircraft on a different flight controller. So this isn't set in stone, but this is a good guide, useful guide to help you understand where to hook all these things up. And in the example that I have here, if you install all these pins, then you can just use like servo connectors to plug things in. So I have a servo here, and if you wanted to hook this, say, to one of these servo outputs, I can just plug it in. Make sure you get the polarity right. Now these are color coded so that you have black for ground, red for power, and then white for signal. So I want to make sure I get the black, or in this case the brown, on the ground. And I apologize for the camera. But anyway, I think you get the idea. You can plug it in. So these pins make it convenient for plugging and unplugging things in if you don't want to solder directly to it. You can solder directly to the board if you want, and in fact you'll wind up having to solder your ESC connection here. So this board was wired up at one time to an ESC. Boy, this is hard to do. Get it in. Okay. So your battery will connect here, and by the way, your battery input will always come into the board and then out to all your peripherals. It's very rare that you would connect anything else directly to your battery, because you want your flight controller to measure the current that you have drawn from the battery, because the flight controller firmware will keep track of how much power you've drawn from your battery to give you an indication of how much capacity you have left in your battery. But there's also a current sensor built into the board here, and that's where it'll measure your current, and over time it measures your amp hour draw or your watt hour usage. And then your ESCs can connect here, and this one had one ESC connected at one time. You don't have to use two if you don't have two, but the board supports two. That's the thing, the board may support more than what you need. You don't need to use everything that's on the board. But again, this is a useful guide for hooking up your system for your particular aircraft. There's information about various components, the UARTs, ADC, I2C, PWM, the connections, the pins, and whatnot. And here's just another, and by the way, if you're using iNav, here at the top it says iNav target, Maytech F765. So when you go to install some firmware onto this particular board, iNav supports many, many different flight controller boards. So if you want the right build of the iNav firmware for this particular board, you want to make sure that you're selecting the right target when you go to burn your firmware into the microcontroller. And that's what you're doing, is you're burning firmware into the microcontroller. So iNav provides a configurator that runs on your computer that you then connect to your computer to this USB serial port here, and then you can burn your firmware on there, and then you can also, once the firmware is on there, you can load the configurator and talk to the flight controller itself. And then there's some options down here where in the command line interface you can actually enter some commands to configure certain things on your flight controller, and this kind of tells you how to do it for iNav. So there's a lot of good useful information in the Maytech documentation. There's some more information, more of the same layout. This may be a duplicate page, and then here's some other close-up here of selecting the VSX, or I don't know, there's some power distribution here where you can select either 5 volts by leaving these unsoldered, or you can jumper these two pads to get 6 volts, or you can jumper these two to get 7.2 volts, and you can jumper this one here to raise 9 volts to 12 volts. Just various options that you have on the board that you can do. So that's the general overview of what's inside a flight controller. In the next video, I will look at actually connecting to one of these through the computer and seeing how you can actually program the flight controller firmware on there and how you can configure it. There's a lot of useful videos and information out on the web. I'm just hoping to provide a sort of quick start on what a flight controller is, and then you can dig deeper from there. I just have a couple of things here. I just wanted to point out real quick that like I said, the I2C or I2C is a bus, whereas the UARTs are individual devices. So you can hook one device to a UART, but you can hook multiple devices to an I2C or I2C bus. So what this little thing does is this end plugs into the I2C bus on the microcontroller, and then I have up to, I think, 10 devices that I can plug into here, I2C devices. Now here I have a temperature sensor. It's just a little printed circuit board with a chip on there that measures the temperature, and I can plug this into this bus, and it doesn't matter actually which one of these pins I plug it into, but I can plug in a bunch of these temperature sensors and put them in various places if I want to, and they can all be driven off the one connection to the microcontroller. Now these are all addressable, and you can define their address. I have some sticky tape on the back of this, so I can't really see it, but on the back there's solder jumpers that you can solder to set the address in here. So you can have up to 8 of these temperature sensors on the same I2C bus, And you could configure your flight controller to show their values in your on-screen display, so you can read various temperatures if you wanted to do that. This isn't the only I2C peripheral that you can hook up. You can hook up a compass. You could hook up any other device that supports I2C. The compass and the temperature sensors are the only two I can think of right offhand. But basically, that is the basic overview of a flight controller and the microcontroller that drives it. So I'm going to wrap this up here, and thank you for sticking this out with me. I hope this was useful. Please let me know in the comments below, and I would appreciate it. Thank you.